Now let us go into the important classes of Fourier series methods. Okay, so first one is trigonometric form and second one is exponential form. Coming to the definition, in the representation of periodic signals in terms of linear combination of orthogonal functions, and if the orthogonal functions are trigonometric in nature, and then that is called a trigonometric form. And if the representation of periodic signals in terms of linear combination of orthogonal function, and if the orthogonal functions are exponential in form, then we call that as an exponential Fourier series method. Today's class is about Fourier series, the introduction on Fourier series. Okay, going to the definition. So we have two kinds of definitions here. The representation of a signal over a certain interval of time of linear combination of orthogonal functions is called Fourier series. Or the Fourier series expansion is used for periodic signals, to expand them in terms of their harmonics, which are sinusoidal and orthogonal to each other. So let us try to understand the definition here. So Fourier series expansion is used only for periodic signals. It is not for non-periodic signals. Okay, so periodic signals are x of t plus t. If this is equals to x of t, then we call it as a periodic signals. So a Fourier series expansion is only for the periodic signals. In the periodic signals, we have again continuous time, discrete time. Okay, so continuous time, the Fourier series expansion is called continuous time Fourier series expansion, and for the discrete time, the Fourier expansion will be discrete time Fourier series expansion. Okay, so Fourier series expansion is used for periodic signals to expand them in terms of their harmonics. Okay, in order to know what is harmonics, we should know what is frequency. We know the term frequency. Frequency can be defined as cycles per second or the rate of change. The rate of change can be called as a frequency. If you take the signal, for example, the expansion, this x of t is a periodic signal. Okay, so let us take the example 3 sine omega t plus 7 sine 2 omega t plus 5 sine 3 omega t. Here, the periodic signal is the sum of the original signal plus the harmonics. Here, the first term is nothing but the original signal or the first harmonic. And the second term is called second harmonic. And third term is called third harmonic. Or else the second term is the even harmonic and third term is the odd harmonic. Okay, so this is the expansion here. Okay, from this you got to analyze it, and this is actually brought out from the waveform. Okay, using Fourier series expansion. So the Fourier series expansion is used for periodic signals to expand them in terms of their harmonics, which are sinusoidal. Okay, they are sinusoidal and orthogonal. As we know, orthogonality is nothing but perpendicular to each other. So this is how you got to understand the definition of the Fourier series. Okay. Not every periodic signal can actually have an expansion of Fourier series. It has to satisfy certain conditions, and those conditions are called Dirichlet conditions. Okay, this Dirichlet is a German mathematician and he has developed this condition. Okay, if you look into the condition 1 is the periodic signal should have finite number of maximas and minima over the range of a period. If you look into the signal x1 of t, which is a periodic signal, okay, and here look in this over range of period 0 to t, and the number of maxima here is 1. In this period, the number of maxima here is 1. 1 maxima. And if you took another period t by 2 to 3t by 2, and the number of minimas which are available here is 1 again. 1 minima. Okay, so the condition 1, according to the condition 1, it should have, the periodic signal should have the finite number of maximas and minima. So according to that, this signal actually satisfy the first condition of Dirichlet. Okay, now look into the other periodic signal. Even this is a periodic signal. But if you look here, over a range of period, the number of maximas and minimas to find is very difficult. Okay, so this doesn't satisfy the condition 1. Okay, even though it is a periodic signal, but to have a finite number of maximas and minimas in this signal is difficult. So this doesn't satisfy the condition 1. Okay, now let us go to the second condition. So now the second Dirichlet condition is the periodic signal should have finite number of discontinuities over the range of period. So here we took an example here x1 of t. If you take a range of period 0 to t, or else here 0 to t. In this range of period, if you look into the discontinuities, it is ranging from 0 to 1 and 1 to 0. And here the discontinuities are finite in nature. Okay, so this signal actually satisfies the condition 2. And look into the second signal. Here the discontinuities is actually varying from a certain height. We take if this width is w and this height is h. And it is constantly decreasing. To this width is w by 2 and this height is h by 2. And it is constantly decreasing up to the infinite values. And here in this signal, in spite of being periodic, but the discontinuities are infinite. There are no certain or finite discontinuities in this signal. So even though this signal is periodic signal, but the condition 2 is the periodic signal should have finite number of discontinuities. So this signal is actually failing to justify the condition number 2. Now the last condition is the periodic signal should be absolutely integrable over a range of time period. Okay, if you look into this periodic signal, the time period of 0 to t, and let us find the integration over a period, and let us know whether it has a finite value or not. Okay, so if you take this example, we will find for this. Okay, over 0 to t by 2, okay, the amplitude is a. So a over x of t, we have a into d of t. So this is equals to a 0 to t by 2 dt, which is equals to a into t by 2, which is a finite value. Okay, which is less than infinity and it has a finite value. Okay, so the last condition is the periodic signal should be absolutely integrable over a range of period. Okay, these are the important condition of Dirichlet's in order to have a Fourier series expansion. Though it is a periodic signal, not every periodic signal can have a Fourier series expansion. Only those periodic signals which satisfies the Dirichlet's condition can only have a Fourier series expansion. In tomorrow's class, we will see the methods of a Fourier series, like trigonometric Fourier series and exponential Fourier series. In yesterday's class, we've discussed about the Fourier series, the introduction of Fourier series, and the conditions What are those conditions? Dirichlet conditions. And today we will explain about the trigonometric form of Fourier series. So it is one of the one method we've discussed about trigonometric Fourier series, and next one will be exponential Fourier series. So okay, in today's class we'll see a trigonometric form of Fourier series and how the coefficients are extracted from the series, and we will look into one problem. Okay, so a sine signal x of t, a sine omega naught t, is a periodic signal with a period t equals to 2 pi by omega naught. Okay, so now also the sum of two sines is periodic provided that the frequencies are integral multiples of the fundamental frequency omega naught. Okay, so the fundamental frequency omega naught and the integral multiple of the omega naught makes it as a periodic. Okay, so we can show that the signal x of t, a sum of sines and cosine functions whose frequencies are integral multiples of omega naught. We will just see how it looks. So x of t will be equals to a naught plus a1 cos omega naught t plus a2 cos 2 omega naught t plus so on, this is t, plus so on, ak cos k omega naught t plus b1 sin omega naught t plus b2 sin 2 omega naught t plus so on bk sin k omega naught t. So we can simplify this as x of t equals to a naught plus sigma n equals to 1 to k an cos n omega naught t plus bn sin n omega naught t. Okay, where a naught, a1, a2, b1, b2 and all are the coefficients. Okay, and in order to make it an infinite Fourier series, we will actually tend n tends to infinity. So that will be an infinite Fourier series expansion. So the x of t equals to a naught plus sigma n equals to 1 to k an cos n omega naught t plus bn sin n omega naught t, where a naught, a1, a2 and b1, b2 and so on, those are constants with the fundamental frequency omega naught. Okay, now let us know whether the signal is periodic or not. So the signal must satisfy this in order to call that itself as a periodic. So let us find whether this is periodic or not. So this will be a naught plus sigma n equals to 1 to k an cos n omega naught t plus t plus bn sin n omega naught t plus t. Okay, where t equals to 2 pi by omega naught. We are aware of this. Okay, so this will be equals to x of t plus t will be equals to a naught plus sigma n equals to 1 to k an cos n omega naught t plus 2 pi by omega naught plus bn sin n omega naught into t plus 2 pi by omega naught. Okay, so this will be a naught plus sigma n equals to 1 to k an into cos n omega naught t plus n omega naught into 2 pi by omega naught, and omega naught gets cancelled. So this will be cos of n omega naught t plus 2 pi n, because omega naught and omega naught gets cancelled, Similarly, plus Bn sine of n omega naught t plus 2 pi n. So cos 2 pi plus theta and sine 2 pi plus theta. So this will be, and there will be no change of value 1 to k. So this will be an cos theta omega naught t. Okay, from the basics, plus Bn sine n omega naught t. Okay, so the periodicity is justified. Okay, the x of t expansion, so the periodicity is justified here. Okay, so if k tends to infinity, if k tends to infinity, then we can actually say that it is an infinite Fourier series expansion. So this is the expansion for n equals to 0 to k. Okay, so the infinite series of sine and cosine term of frequencies a naught, 0, w, omega naught, 2 omega naught and k omega naught is known as trigonometric form of Fourier series. We will look into the representation now. It states that x of t will be equals to sigma, where n equals to 0 to infinity, an cos n omega naught t plus Bn sine n omega naught t. Okay, so if you substitute the values, if n equals to 0 here, a naught cos 0 value, which is 1. So I'll bring it out a naught here. If you substitute the same n of 0 here, it is b naught sine 0. So the total value will be 0. That's the reason we only get a naught term and not b naught. Okay, a naught plus, I can simply write n equals to 1 to infinity. This will be again an cos n omega naught t plus bn sine n omega naught t. Okay, after substituting the values, if n equals to 1 here, a1 cos omega naught t plus b1 sine omega naught t. So that will be first harmonic. Okay, if we substitute n equals to 2, then it will be a2 cos 2 omega naught t plus b2 sine 2 omega naught t, and that will be the second harmonic. If you substitute k, similarly it will be kth harmonic. Okay, and the values a naught, a1, a2 and b naught are constants. Okay, so a naught here is called as a DC value, or else the average value. So from the expression, we will try to evaluate the terms a naught, an and bn. Okay, in order to determine a naught, you have to integrate the x of t over the period t naught to t naught plus t. Okay, in a period t naught to t naught plus t, where the arbitrary time is t naught. Okay, so we will see how it is done. Okay, so you just keep this aside, it is integrable and we will find it out. Here, integral t naught to t naught plus t and sigma n equals to 1 to infinity an cos n omega naught t plus bn sin n omega naught t we will determine now. Okay, so we will leave this aside, it is integrable as I said. So only this part I am doing. Okay, so this will be sigma n equals to 1 to infinity a n integral t naught to t naught plus t cos n omega naught t dt plus sigma n equals to 1 to infinity bn integral t naught to t naught plus t sine n omega naught t dt. Okay, integration of a cos term or a cosine term over a period. Okay, the area under this period, if you find it out, it will be 0. Okay, similarly this one, for any value of n and t. Okay, for any value of n and t, this term will be 0 and this term will be also 0. Okay, so and coming to the first part, this will be A naught is a constant, we'll bring it out, and integration of T naught to T naught plus T dt. So this is T, you get the value of T, and in the value of T you substitute T naught plus T and T naught. So it will be A naught into T naught plus T minus T naught. Okay, these values gets cancelled, and this value is anyways 0. This is 0, 0 into this, and this is 0, 0 into this. This whole term is 0. So this will be equals to integral T naught to T naught plus T x of T dt. But you want the value A naught. Okay, so bring the T to the other side. So A naught will be equals to 1 by T integral T naught to T naught plus T x of T dt. So this is how you evaluate the term A naught. Okay, so similarly we will determine how to evaluate An and Bn. So we've evaluated the value A naught. Now we will see how we're going to evaluate An. Okay, in order to evaluate An and Bn, we will use some results. Okay, so integration T naught to T naught in the period T naught to T naught plus T cos n omega naught T into cos m omega naught T dt will be equals to 0 when these two values are different. I mean n and m, if they are not equal, then the answer is 0. Okay, if at all this, I mean the n equals to m, what will happen? This will be cos square term. Okay, cos square term will be written as 1 plus cos 2 theta by 2. If you integrate that 1 plus cos 2 theta by 2 in the period T naught and T naught plus T, you will get the value T by 2. Similarly, for the sin n omega naught T and sin m omega naught T. If n and m are not equal, then the term will be 0. If n equals to m, then it will be sin square theta. Okay, sin square theta can be written 1 minus cos 2 theta by 2. In a period T naught and T naught plus T, if you integrate, the value will be T naught by 2. And the other term is, other result what we use is, in the integration in the period T naught and T naught plus T, the term sin n omega naught T and cos m omega naught T, at any value of n and m, the value will be 0. So we are going to use these three results to evaluate An. Okay, so in order to evaluate An, like in the earlier case, we will multiply the whole multiply the x of t with cos m omega naught T and integrate over a period. Okay, we will see how it is done. Okay, so this is the expansion, and we will integrate in a period T naught to T naught plus T x of t into cos m omega naught T dt. This will be equals to integrate T naught plus T A naught cos of m omega naught T dt plus integrate T naught, integration T naught to T naught plus T sigma n equals to 1 to infinity An cos n omega naught T into cos of m omega naught T dt plus integration T naught to T naught plus T sigma n equals to 1 to infinity bn sin n omega naught T into cos of m omega naught T dt. Okay, if you just if you still want to expand this for our convenience, we will write this is T naught to T naught plus T. You bring A naught outside, and this will be cos m omega naught T dt. This whole term will be 0 now. Okay, and this will be sigma n equals to 1 to infinity a n, and then integration T naught to T naught plus T cos n omega naught T into cos m omega naught T dt plus sigma n equals to 1 to infinity Bn, the integration T naught to T naught plus T sine n omega naught T into cos of m omega naught T dt. Okay, so here we have some results and we're going to use it here. So this term will be total 0 because the area under or a period at any value of m and t, it will be 0. So this whole term will be 0. Coming to here, this is integral t naught to t naught plus t sine n omega naught t into cos m omega naught t. So this will be 0 for all the values of m and n. Coming to here, okay, for different values of n and m, if n not equals to m, this whole term will be 0. But there is a point where n equals to m. In that condition, we have a value called t by 2. So we are going to simply substitute that value, okay, when n equals to m. Okay, so this whole term will be now, so this term will be 0 and this term will be 0. This term, if n is not equals to m, okay, because we have values here at n equals to 1 to infinity value, at one point if n equals to m value, and then this condition will exist and the other whole terms, the whole terms will be 0. So we're going to put it now. So this will be, integral t naught to t naught plus t x of t cos of m omega naught t dt will be equals to 0 plus at n equals to m value, okay, I'm going to substitute a m value, okay, and here at n equals to m value cos m omega naught t value, okay, at that condition the whole integration in a period will be equals to what? T by 2. I am simply substituting t by 2 value here. Okay, and now at n equals to m, so even at the n value we will replace it with n now. So a m is nothing but a n now, so at m equals to n, so equals to 2 by t integral t naught to t naught plus t x of t into cos of m omega naught t dt. So this is how you're going to evaluate the an, okay. Now we will see how to evaluate Bn, okay. Similarly, like the previous evaluation, what we have to do here is we will multiply the whole expression with sine m omega naught t, okay, and integrate over a period, okay. We will see how it is done, okay, in order to evaluate Bn here. So we will integrate t naught, in the period t naught to t naught plus t x of t, and we will multiply with sine m omega naught t dt. So this will be equals to integration in the period t naught to t naught plus t a naught into sine of m omega naught t plus integral in the period t naught to t naught plus t sigma n equals to 1 to infinity a n cos n omega naught t into sine of m omega naught t dt plus integral in the period t naught to t naught plus t sigma n equals to 1 to infinity Bn sine of n omega naught t into sine of m omega naught t dt. Okay, if you look into the first term dt, okay, first term, this whole term will be 0, okay, area under the period t naught to in the period t naught plus t, this whole term sign will be 0. So this will be equals to, okay, this term will be 0, and this term cos n, the integral cos n omega naught t into sine m omega naught t. If you look into this result, okay, integral in a period sine n omega naught into cos m omega naught t dt equals to 0 for all values of m and n. So this whole term will be 0. Okay, this term will be 0 and this term will be 0, where this term will exist when n is equals to m. Okay, if you look here, this result at n equals to m, the value is t by 2. If n is not equals to m, then it will be 0. Okay, so I will simply write this as t naught to t naught plus t x of t sine m omega naught t dt will be equals to, this whole term will be 0 and this term will be also 0, but n equals to m only at when n equals to, okay, we'll bring this out. So sigma n equals to 1 to infinity bn integral t naught to t naught plus t sine n omega naught t into sine m omega naught t dt. Okay, so at n equals to m, okay, if it is that, then it is bn sine m omega naught t into sine m omega naught t. Only in this period, only in that case where n equals to m, this whole term will be t by 2. We will substitute that. So then it will be equals to t naught plus t x of t into sine m omega naught t dt will be equals to bm, and this whole term will be equals to t by 2, cause where n equals to m. So we are replacing the n value with m. That is okay. You can also replace it back by putting it bn equals to, you bring this to the other side, then it will be 2 by t integral t naught plus t x of t into sine of m omega naught t t. So this is how we are going to evaluate the value Vn. So this a naught, am and bm are the Fourier series coefficients. Here what we have done is we've actually multiplied the expansion with cos m omega naught t in order to determine am. Okay, and sine m omega naught t we've multiplied and also integrated in order to get bm values, but at n equals to m, so those are interchangeable. So this a naught is a naught, and here we can change this value to an, and this will be an. Similarly, this will be sine n, and this will be bn. So using this coefficients, we will try to solve a problem.